All right. Welcome back to the interactive session of the course Viscous Fluid Flow. So we begin by understanding this week's contents. So let's quickly revisit what we saw in the previous week. So in the last week, we solved the problem. So basically, we solved a flow field that comprised of a flow that is being generated by rotating porous cylinder, and our system was basically something like this. So the cylinder rotated in the counterclockwise sense with an angular velocity, with a constant angular velocity omega, and the nature of the surface is such that there is a constant radial suction that is being taking place in the r direction uh, of the coordinate system. And the idea was to basically evaluate the flow field generated because of this rotation and a constant suction. So we started off by writing the various non-dimensional scales, or writing the various characteristic scales of the velocity. Let's say we saw that we had two characteristic scales of the velocity that was given to us. The radial velocity was scaled as the suction velocity, while the angular velocity, that is the u theta characteristic, was scaled as the rotational velocity of the cylinder times its radius. And then we had the definite scaling for pressure, which is basically the advection scale that we considered here. And the length scale was basically the length and the radius of the cylinder. So the idea first task was to derive non-dimensional equations of its dimensional counterparts by using those characteristic scales. And we started off by deriving the r momentum equation, plugged in the characteristic scales as you can see here, and then went on to eventually derive the non-dimensionalized r momentum equation, which is basically given by this equation 1. So as you can see in equation 1, it's completely non-dimensional, and we have a constant u tilde, which basically signifies the strength of the rotational characteristic velocity to the suction velocity, or it's the characteristic velocity in the r direction. So in other words, it just takes into account of the fact that how fast is the rotational velocity of the cylinder in comparison to basically the suction that is being taking place on its surface. And its ratio is basically described by this quantity u tilde. And we also end up getting this Reynolds number, which is basically defined in terms of its suction velocity. In addition to this, we solved the theta momentum equation because now we knew we had actually three unknowns: the two velocities in the r and theta direction, and the pressure. So basically, we need three equations. The first two equations were basically the r and the theta momentum equation, and the third equation was the continuity equation that we actually solved for. So the theta momentum equation, by plugging all the characteristic variables, simplified to equation 2, as you can see here. And then we use the continuity equation by invoking all the assumptions, and it ended up basically giving us the radial velocity, which is just minus a 1 by r by using the boundary condition on its surface. Then what we did is we used the flow field, that is the r direction flow field, and plugged it into the theta momentum equation to basically find out u theta. There we saw that we eventually had to solve an equidimensional equations, and I would yeah so I was just recapitulating what we did in the last week. So the thing is, we solved the theta momentum equation by plugging in the r velocity field, which was basically minus 1 by r, and we saw that we ended up getting an equidimensional equation of this form. Not this exactly, we end up getting an equidimensional equation of this form basically. So sometimes these equidimensional equations are also known as Euler's equation, and they are often solved by considering the variable to be of the form some r power alpha, or let's say some r power k, and we end up having a equation for k where essentially the roots of the variable k, or basically the roots of the characteristic equation here, gives us the entire solution basically, by considering the individual contribution from all the roots and keeping in mind that they are linearly independent of each other. So the the physical picture is that we end up getting this u theta, we end up getting this u theta as a function of r, which basically came out something like this. And then we saw that under a special case when Reynolds number is basically less than 1, we eventually could find out the exact solution for u theta, which came as to be 1 by r. So now, as I said, we stopped it here. So we derived the expressions of or expression for u r and u theta. And the idea was that now we need to derive an expression for the pressure. So the idea is basically to use the expression of u r and u theta in basically the r momentum equation, because we know that pressure will only vary along r, because the problem is inherently axisymmetric in nature in cylindrical geometry. So this means pressure will just be a function of r, and we need to use the expression of u r and u theta in the r momentum equation to get how the pressure field would look like. Okay, so this is the idea, and we will now continue from where we stop. We will use the expression of u r and u theta in equation 1. So this equation 1 is basically the r momentum equation. So before, like starting from where we stopped in the last week, I would wait here for a couple of minutes. If you have any doubts, you can ask me based on this or anything like related to the assignments or the sessions. If not, we will start off with this problem, like from where we left, and finish up this problem. And I'll also share an insightful insight on existence of solutions here, because I think you asked it in the last class. Then what happens when Reynolds number is basically greater than 1? So we will see this case that there is also a stronger like criteria for finding out finding out the spatial solutions for this case, as we will shortly see. All right. If you don't have any questions, we will begin by trying to solve the pressure field. So the idea is, so I'll just write it once again. So we got UR bar, which is the non-dimensional radial velocity, as minus of 1 by r, and we got U theta bar as 1 upon r. So we will substitute this in the r momentum equation. So let's see what is the r momentum equation. It's equation 1 to be precise. Yeah, so we will substitute the value of ur and u theta in this equation. And then, so for that, what do we need? We need these derivatives. Okay, we basically need these derivatives. So we'll calculate this and then substitute it. Okay, so let's do this. So before substituting, we also need one term, which is basically d of ur bar by dr. And this should be what? This should be just 1 upon r squared. Okay, so this means this r times du bar by dr bar in equation 1, as we saw just now, will eventually come out to be what? This will come out to be 1 by r. Okay, so this means now let's evaluate the terms here. So let's go to equation 1 once again. Okay, so this is the theta. Yeah, so what do we need? We need this term, which is ur into this. So this is basically ur into dur by dr. We will have this term. This term is already known. U theta is already known. U tilde is just a constant. We just need to evaluate this term as well. So let's first do this. Okay, let's just first. So this is just mathematics. So it just there is nothing to explain here. So it's just substituted and nothing else. So what I was telling is we also need to evaluate this term for the viscous force, which is dd r bar. So these are all bars here. So dd r bar into r bar times dur bar by dr, and as you can see, this will simply come out to be of minus of 1 by r squared. I think this is correct. Yeah. Okay. All right. Okay. So now if you just plug in these terms in equation 1, okay, in equation 1, we will end up, I'm just directly writing, we'll just end up getting 1 upon 1 by r bar cube minus u tilde squared, because remember u tilde is just a constant. It is just the strength of the rotational velocity, characteristic rotational velocity to the strength of the like suction velocity. So it's just a constant. So it is u tilde squared by 1 by r cube, and On the right hand side, we have the pressure gradient, which was basically u tilde into dp by dr with a minus sign. Plus, if you simplify the viscous term, it will just turn out to be minus 1 by r cube plus 1 by r cube into the. So yeah, so just 1 second, we'll cross check it if it is correct or not. So so I think no, this was the theta momentum equation. Yeah. So this term, this oops. So this term essentially came out to be what? This term came out to be, so this term came out to be minus of 1 by r squared. Okay. Sorry, I mean this term came out to be minus of 1 upon r squared. So there is this multiplied with 1 upon r. Okay, so this will become, so this term will in turn, the whole term will become minus of 1 by r cube. Okay, and if you simplify this term, it will just become 1 upon r cube. Since u r is basically minus of 1 by r. Okay, so this entire term will become 1 upon r cube. So this 1 upon r cube and minus of 1 upon r cube will cancel each other. I hope you get the math here. You can do it yourself and check it out. So this term would basically cancel each other. That's what I want to say. And there is this 1 upon Reynolds number, which was multiplied here. All right. Okay, so there is 1 upon Reynolds number, which was multiplied here. But nevertheless, this 1 upon r cube and 1 upon r cube would cancel each other. And there is also a bar here. Okay, there are bars here because it's non-dimensional. All right, so we just end up getting what? So we just end up getting r bar cube, okay, into 1 plus of q tilde squared, and the minus sign would just cancel from both the sides. So this would be u tilde into dp bar by dr bar. Okay, so is this equation integrable or not? Can you tell me? Is it directly integrable or?
Yes.
Yeah, exactly. So this is integrable, right? So what we will do is, because u tilde is just a constant, so what we will do is we'll bring the pressure into one side, okay, and we'll bring the constant terms into the other side. Into this is just dr by r cube. I hope the math is clear. Okay, so this pressure term we kept in one side, and this term we just brought in the denominator. So now if we integrate it, okay, let's first do indirect integration, and we'll have a constant over there. So if we integrate it, this would become what? This would become pressure, which is p bar, okay, and this would be 1 plus of u tilde squared by u tilde would come out because it's a constant, and this would be, so integration of x to the power n is x to the power n plus 1 by n plus 1. So if you do that, it would just be minus of 1 by 2r squared, okay, if I'm not wrong, plus a constant. Just let me know if I just made a mistake, but I hope I'm right.
In denominator, shouldn't it be 1 by u tilde square?
Yeah, it should be 1 by u tilde squared. Okay, let's check. Okay. So no, this u tilde is basically came, so this u tilde came from here, right? This goes down. That's why this u tilde.
I mean the dp bar by dr bar u tilde square is multiplied.
Acha, okay, this there is an u tilde squared here. Okay, I didn't see that.
Yeah.
Okay, let's check it out. Okay. I think it has to be u tilde squared only. Oh, let's check it out. No, I don't think so. There is an u tilde squared here, right? There's just u tilde here. Just u tilde, right? This term.
I'll check it once.
Yeah, I think there is just u tilde present there. I'll also check my notes. Maybe I don't think I have my notes here. But anyways, it's just a matter of a constant. So yeah, just check it out. But I don't think so. It will create any significant qualitative change in the calculations. I think it's just u tilde. You can just check it out. Yeah. So basically, the idea is we integrated this. Check it out. It will be just u tilde or u tilde squared. But anyway, this term is just a constant, so it will not basically come into the I mean, it will obviously qualitatively change pressure. It might change pressure, but quantitatively our calculations won't be affected. Sorry, the other way around. Like qualitatively, it it will not be affected. That's what I want to say. This. Okay, so the idea is we need to evaluate this constant. Okay, and of course this is R bar. So so for evaluating this constant, we need the boundary condition, of course. So the boundary condition, as if you remember, it was something like this. So the pressure when this R bar tends to infinity, uh, that is the pressure at far field, this was basically equal to the atmospheric pressure P naught, which means if I impose this boundary condition here, so what do we get? So this means if I impose it there, this means we will now look at this term when R bar tends to infinity, which means this would just drop out, and so this would just drop out. Okay. Okay. Did I see if I do it currently? Fine, yeah. So this means that at R bar tending to infinity, this term would just drop out, which means the constant, as you can see, the constant would basically come out to be P naught. I hope this is clear.
But one
Yes.
doubt. P
Yeah,
was equal to P naught. So P bar is a non-dimensionalized part. So
correct.
it
Yeah.
should be P
Yeah.
naught by rho omega square is good.
Yes, 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 yes. Correct. Ha ha ha. Yes, you are right. Yes, I think you are right. Yeah, because yeah. So what you mean is, yeah, I understood. So the dimensional pressure when the dimensional radius goes to infinity is basically P naught. So if I just non-dimensionalize it, it becomes PC. Okay, and this becomes the non-dimensional pressure, and this is the non-dimensional radius, of course, and this is P naught. So P bar when R bar goes to infinity is basically P naught by PC, and PC was nothing but rho times omega squared A square. Yes, you are right. So this means this P bar would be just P naught by rho times omega squared A square. That is simply because this P bar is a non-dimensional quantity, which means thank you for the like correction. Which means, so what does it mean? This means that this constant will eventually come out to be P naught by rho times omega squared A squared. Okay. And then what you can do is you can just name it as some P naught bar. Okay, where P naught bar is basically the atmospheric pressure scaled with the characteristic pressure. That's it. So this means now you have got the pressure field. So the pressure field P bar as a function of R bar is basically what? So it's just minus of 1 upon 2 R bar squared, okay, into this term 1 plus U tilde squared by U tilde. All right. Plus there is this P naught, and this P naught is basically plus this is basically P naught bar. Where P naught bar is the scaled atmospheric pressure, as we have pointed out. So this means we are done with the solution for pressure, and this is the final part of the question. Okay, that the that is what the question asked. So this is basically the solution for the pressure field. Okay. So this means that P bar minus P naught, which is basically the gauge pressure, or it's the scale pressure that we say, it varies as 1 upon r squared, as you can see, 1 upon r bar squared. So it's interesting, right? So the velocities, as you saw, it varies at 1 upon r, and pressure, in fact, it varies at 1 upon r squared. Okay, so the pressure field would basically die out more rapidly than the velocity field, and this is one thing that we can conclude from this observation. Okay, before ending this question, I would answer a doubt that you asked in the last class, that what happens when Reynolds number basically becomes greater than equals to 1, because we said that this solution was only valid, this particular solution, or the fact that this u r and u theta is equal to 1 upon r and minus 1 upon r respectively is only valid when Reynolds number was basically less than equal to, it was, or it, so it's the condition that when Reynolds number was less than, it was less than 1. So what happens when Reynolds number is greater than 1? So I would put this in a different way, and I'll show it that a stronger uniqueness of this solution. So this means that when Reynolds number was greater than 1, we had infinitely many solutions, right? Or an unique solution is not possible. I would say we can access this problem, we can access the uniqueness of this problem up to a further higher Reynolds number by defining something, okay, which is known as the circulation parameter. Okay, so there is some, so I'll just write it as something like this. I'll just write it as a note, and I'll say it's a stronger, I'll just say it's a stronger criteria. Stronger criteria means now we can access a higher NL number in order to get a unique solution, as you will see shortly. So I'll just say it's a stronger criteria for uniqueness of the solution. Okay, so what we will do is we'll define a parameter gamma, okay, which is known as the circulation parameter. So can you tell me if the cylinder, or if there is a rotational velocity u theta, okay, which is basically a function of r, and I define a circulation parameter gamma, what is the relationship between this gamma with u theta? So can you tell me? Yeah,
U theta dl, integral u theta dl.
yeah, exactly. So what, yes, you are exactly right. This means that if I integrate u theta, okay, over this length, where this length, so this is the closed surface integration, which means I'm integrating around the perimeter. Okay, that's what you're saying, right?
Yeah.
Yeah, so this will give us the circulation, and this is one of the, this is one of the most important parameter that uh, I won't say it's the most important parameter, but it's one of the most useful parameter when you are basically looking at flows which are basically possessing this axisymmetricity, and they are rotating around the fixed point or things like this. So the circulation parameter sometimes is of great help to us, as in this case we will see. So if I just simplify this for our problem, this would simply becomes u theta as a function of r into 2 pi r. And then this gamma will also be a function of r, which, and this definition of gamma, it means it is valid at each and every point of r, or it's valid at each and every point of the radius. Okay, so now if we define circulation as something like this, and then we say that, so and that's what, so this is just one definition of circulation, but how do we use this into our problem is something that we will see. So let's name this as equation, what, maybe we'll name it as equation 6, let's say. Okay, so now what I say is, when this radius, I'll just say it's r bar because we are all dealing with non-dimensional problems. So this is just bar quantity. So the boundary condition is that gamma, when r tends to infinity, tends to a finite value, and we'll say this is gamma naught. Okay, so this means that the circulation is basically bounded. Okay, that's the other way of saying that gamma, when r tends to infinity, is a finite value. Okay, so I would say this is the boundedness condition. Okay, and we will use this bit of information to find a stronger or to find a broader range of Reynolds number, up to which we'll find a unique solution for the problem. Okay, so now what we will do is we will use this and the definition of u theta to basically formulate our problem. So if you remember u theta, okay, so u theta, or in fact it was u theta bar, was in terms of the constant. If you remember, it was something like this. So it was a1 upon r bar plus a2 into r bar into 1 minus of Reynolds number. So from where did we get it? We got it by solving the theta momentum equation. I'll just show you as a recap. So basically we got it from here. So we solved the theta momentum equation, which is basically this. Okay. And then we solve the equidimensional equation to find u theta, and u theta came out to be something like this. That's what exactly I wrote here. All right. Okay. So if u theta is basically that, okay, if u theta is basically this, and then we use this definition, okay, of circulation, then what do we get? And use the fact that circulation is related to u theta as something like this. So then what do we get? So we get, so let's see what we get. So we get 2 pi, okay, into u theta bar. So u theta bar is a1 by r bar plus a2 into r bar to the power 1 minus of Reynolds number, okay, and oops, there has to be a 2 pi r bar because we have used basically this definition, okay, and this was equal to gamma, okay, and at r bar tending to infinity, we know that this 2 pi r bar into a1 by r bar plus a2 into r bar into 1 minus of Reynolds number is basically gamma naught. So from where did you get? This is basically this condition, the boundedness condition, that the circulation ceases to a fixed value when r bar tends to infinity. Okay, which means if I now multiply, if I put this r bar into the, so I just bring this r bar here. So what do we get? So we get 2 pi into a1 plus a2 r bar into, what do we get? We get, I think, 2 minus Reynolds number, okay, is equal to some gamma naught, and I just rearrange certain terms, which means I get a1 plus a2 into r bar into 2 minus a Reynolds number is basically equal to gamma naught by 2 pi. All right. So now, can you tell me? So now, based on this equation, can you tell me that up to which value of Reynolds number, or what is the condition on Reynolds number for which we will get an unique solution based on this definition?
RE greater.
Re greater than what? So I would write here, for unique solution, what is the condition? So yeah, you are, so it's obviously there will be a limit on this Reynolds number, but what is that limit? Is it Re? So is Re greater than some value or Re less than some value? Can you just have a, so just see this equation, just see this equation, just see the, yeah,
Greater than 2.
yeah. So Re greater than 2, Re greater than 2 will have unique solution. Is that what you're saying?
A1, yeah. A1, I mean, A2 will,
Yes.
A-
Yeah,
A2 will be arbitrary and A1 will get uniquely.
Yes, actually, it's the other way around. So have a close look. I mean, your thinking is correct, but I think there is this thing. So you have a close look here. So what happens when RE is greater than 2? Okay, this means that when RE is greater than 2, this term will not blow up, right? You understand blowing up. This means this term will never go to infinity, which means this A1 and A2 are now both unknown, and we just have one condition on basically, which is the surface velocity. So this means we have one
Yeah.
boundary condition and we have two unknowns A1 and A2, which means for RE greater than 2, we will have infinitely many solutions. Did you understand?
Yes.
Infinitely, yes. So what they said. So we'll have infinitely many solutions. Okay. However, if RE is less than 2, then what happens? So if RE is less than 2, okay, then 2 minus RE, if RE is less than 2, will always be greater than what? It will always be greater than 0, right? So this means at r bar tending to infinity, this term, when RE is greater than, when RE is less than 2, will always blow up, which means the only way to have a constant in the right hand side is that A2 has to be equals to 0. Okay, this means for RE less than 2, I hope this is clear. We did this analysis many a times in the previous problem as well. So I hope this is clear. If it's not clear, just stop me at any point of time. So what I was saying is when RE is less than 2, this means the only way we can have a bounded value of circulation is when A2 becomes equals to 0, right? Or else like the left hand side will never be equal to right hand side. Okay, so that's the idea, which means this means that A1, so yeah, so A2 then has to be equal to 0. Okay, this means our only unknown, so the only unknown that we have is A1. Okay, and how do we calculate A1? That is again the same procedure. We use the boundary condition of U theta. So what we know is we basically use the boundary condition here as we did in the last class. So what we know is when U theta at R bar equal to 1 is basically equal to 1, which means you can see that A1 is nothing but 1. Okay, this means we end up getting the same solution, that U theta is 1 by R, as we should get. This is expected because if U theta is 1 by R when R is less than 1, this means that U theta cannot have a sudden jump in its solution. Okay, so this means that U theta is 1 by R uh, for, I would say, for RE less than 2. So this means that so the thing is, if we use the boundary condition on circulation, we can access a little bit broader Reynolds number. But for Reynolds number greater than 2, we will have infinitely many solutions, and this is not in the scope of analytical techniques to find out the solutions of this problem. Okay, so that's the idea. Like as you asked it, that what happens when Reynolds number is greater than 1, we can define circulation and access up to Reynolds number equal to 2, or in fact Reynolds number, let's say, less than 2, in the, I would say, in the neighborhood of 2 maybe. But if it's greater than 2, let's say for Reynolds number equal to 10, or let's say 12, we will have infinitely many solutions, and it's not in the scope of analytical treatment. And for that, like, we need to go for some numerical tools or things like that. Okay, but nevertheless, the idea is yeah. So this would be barred anyway. So the idea is like for Reynolds number less than 2. So what we got is so the velocity fields are like this. So u r bar came out to be minus 1 by r bar. U theta bar, this came out to be 1 upon r bar. And pressure, what do you get? So pressure p bar as a function of r bar, we got it to be what? So we got it to be p naught minus 1 plus of u tilde squared by 2 u tilde r bar squared. Okay, so this is what we got for the pressure, and these are basically the velocities. Okay, where I repeat, this u tilde is basically what it is, omega a by the suction velocity. Okay, so this is basically the u tilde. All right, so this is the final answer of the questions. Uh, that what they're asking for. They ask us for the velocity fields. These are the two velocity fields, and these are the two pressures, basically. Okay, so this is up to which the question ends. So now we'll begin by discussing our contents for this week, week 7. But if you have any doubt of this question up to here, uh, you can revisit the question by yourself and just think about how the procedure is being done. And if you have any doubt, you can basically address. I mean, I'll be happy to address it. All right. So just have a look at your notes and just revisit the problem, and like so this was the involved problem. It was a bit long. I understand that, but these kind of problems are like of great practical use. There is this constant suction that is being taking place when the cylinder is rotating or things like that. And yeah, so like, and also these problems helps us to get insights if we have analytical treatment. So that's the beauty of analytical treatment, is that you get certain insights which you otherwise don't get if you're using some commercial tools, like maybe some commercial tools that are available in the market. So yeah, that's the idea. Anyways, we'll stop here for some time. If you had any doubts, you can let me know, and then we will begin by this week's contents. All right. So in this week, we will discuss a specific class of problem in fluid dynamics, which is known as creeping flows. I think I have mentioned this in the last class, that when Reynolds number basically is very much, so it's very, it's when Reynolds number is basically very much less than one, this, so we end up getting a special class of problems, which is known as the creeping flow problems. And we will discuss this creeping flow, and maybe in this class or in the next class, we will solve one problem that is associated with creeping flows. So in the lecture session, I think we have solved these creeping flow problems, and you have found out, yeah, I think it was done before the lubrication theory. So basically, you have found out that if there is a sphere, okay, if there is a sphere that is basically immersed in a flow, in a uniform flow, which may be coming from far field with a velocity u, then in the limit of creeping flows, that when Reynolds number tends to basically 0, you found out that the force is nothing but some 6 pi times the mu, which is basically a velocity, times the characteristic dimension of the sphere. and and I think that's only. So did you remember what was the expression of force? I think it was 6 pi mu lc rc. I think that's the expression of force that you basically got. So that expression, so I believe you must have followed the detailed derivation. So I think you followed the stream function approach for that. But anyways, so that expression basically stems from the fact that our Reynolds number is very much less than 1, which means that the force, if the sphere is kept constant and there is a flow which is coming at u, so the force that the sphere would experience if we want to hold the sphere stationary is nothing but that 6 pi mu times the radius of the sphere. Maybe that's what you basically got. Okay. So that analysis actually comes from the fact that we are in that creeping flow region. So what we will do is we will revisit the creeping flow equations basically. I mean, you know this, but anyway, we'll revisit them, and then we will discuss one interesting aspect of creeping flow, which was not essentially covered in the theoretical, I mean, in the week's theoretical class, is that because of the inherent nature of the creeping flow equations, which is basically the fact that the creeping flow equations are linear, we can draw certain fascinating conclusions from it, which is otherwise not possible if we have the inertia term in the Navier-Stokes equation. Okay, so that's what I have said, that we will see some general consequence of linearity of the creeping flow equations. And if you want to read more, so since this is a bounded class, we cannot go on and just go on with the discussing one particular topic. So if you want to read more on this topic, you can follow this book by L.G. Gary Leal. So Professor Leal is he's so Professor Leal is a faculty of University of I think San. So I think he's in university. So he's a professor in the University of California, I guess, which is at Santa Barbara. Maybe I may not be correct, but he wrote this nice book, which is the Advanced Transport Phenomena, and it is published by the Cambridge University Press. And if you want to read more on these creeping flows, you can visit chapter 7. I'll write down here. So it's in chapter 7, okay, of this book. and then you can read more on this. So this chapter is it's a fascinating chapter on low Reynolds number hydrodynamics. And do you know why low Reynolds number hydrodynamics is much preferred? Because if you want to study, let's say the screaming motion of a bacteria, or let's say the screaming motion of a flagella. Okay, so these microorganisms have length scale of the order of, let's say, 10 to the power minus 6. Okay, which means if I want to evaluate the Reynolds number, so what is the Reynolds number? It is rho times u times the characteristic dimension by mu, right? So if this length scale is of the order of 10 to the power minus 6, then our Reynolds number typically is very much less than 1, which means we can invoke the creeping flow equations in order to study their dynamics. Okay, and that's why the creeping flow limit is very much essential in this particular field of fluid mechanics. And yeah, so that's the basic idea. Okay. But yeah, so we'll begin with this. So if you have any doubts on this, you can ask me. So we'll begin. I hope the objective of why we are interested in creeping flow equations is clear to you. So yeah, we'll begin. So we'll begin from the very basic. So we'll begin with the very basic Navier-Stokes equation, and then I will write. Then I will show you under what conditions we reach the creeping flow limit. So if we start off the Navier-Stokes equation in the dimensional form. So what does it look like? This rho times, I will just not specify any particular coordinate system. I'll just write down in its vector form. So it becomes rho times del u bar by del p plus, can you tell me what the second term here in vector form?
Is u dot grad u.
Yeah, exactly. So it is just u dot grad u. Okay. By the way, can you tell me this? So this is just a like test of how much you have learned in this course. It's okay like if you can't come up with the answer, but let's see that you know that gradient of a scalar. So what is gradient of a scalar? Is it a scalar or a vector?
Vector.
Yeah, so it's a vector. Let's say it's a vector v. Okay, so then what is gradient of a vector? Is it a vector, or is
Tensor.
it? Yeah, exactly. So this means that this grad u is basically a tensor. If you want to write this in index notation, it is just del ui by del xj. And you know that if we have two free indices in a representation, then it is known as a tensor, which means that this grad u is basically a tensor, and this whole term, if you write in index notation, it is just something like this. So it is uj times del ui by del xj. Okay, so that's why, so this whole term, if you write it in index notation, is basically ui times del ui. Sorry, this. So I'll just write it like this. So this whole term is basically uj times del uj by, sorry, making the same mistake again. So it is uj times del ui by del xj. So then, how many free indices do we have here in this term? So you understand, right? The difference between a free indices and a repeating index. So do you know this? Like the Einstein summation
Two.
rule?
Two.
No,
INJ.
no, that's not. So I'm asked. So no,
Three.
that's not the. Yeah. So
Are you asking number of terms?
no, no. I'm asking how many free indices do we have here?
One. I.
Yeah, exactly. So this I is basically a free index. So any index which doesn't repeat with itself is known as a free index. Okay. And the number of free indices denotes the order of the like quantity. If we do not have any free indices, it is known as a scalar. If we have one free indices, it is known as a vector. And if we have two free indices, it is basically a tensor. Let's say we have four free indices, it's a fourth order tensor. Okay, and so on and so forth. So this means that that's why this u dot grad u is essentially a vector, and you can also prove it like this from the Einstein convention rule. But yeah, nevertheless, this was not the part of the discussions. I just want to bring it up as a revision of the NS equations. Okay. So nevertheless, this term was basically rho times del u by del t, or dou u by dou t, plus this term. And then what do we have? We have the pressure gradient, so that's why this becomes gradient of pressure. Okay, plus if we just follow that it's a Newtonian fluid, it will just be del square u bar. Okay, and also we have this So remember, when you are writing the Navier-Stokes equation, it should always be coupled with the continuity equation, and the continuity equation is nothing but divergence of u equal to 0. Okay. So now what we will do is we'll try to non-dimensionalize this equation. Okay, and let's see what do we get. Okay, so let's see. We choose.
Mu will come on right side.
Yeah, exactly,
Mu
exactly.
del.
Yes, yes. Mu will come here. There has to be a mu here. Yes. Okay. So yeah. So now if we non-dimensionalize, and let's say just for the sake of simplicity, I denote the dimensional terms. Okay, I denote the dimensional term as, so these are dimensional terms, right? These are just dimensional terms. Okay, and in this analysis, I will denote the dimensional term as just dash terms. Okay, because since we are dealing mostly with non-dimensional terms, so I want to make the non-dimensional terms simpler to look at, and that's why I'll just write it as some dash terms. Okay, so this is, yeah, so this is dimensional gradient, this is dimensional divergence. Okay, this is dimensional pressure, and yeah, that's it. So now if I define a non-dimensional u, okay, this will be the dimensional u by characteristic q. Okay, and let's just keep the characteristic q as just uc. Similarly, if I define a non-dimensional time t bar, okay, it will, sorry, if I define a non-dimensional time t, then this would be the dimensional time t dash, okay, divided by the characteristic time tc. This characteristic time may be the advection time scale, or this may be the inherent time scale that we saw in the previous problem, or it may be the ratio of the characteristic time scale to the inherent time scale. Okay, I mean, it may be the ratio of this advection time scale to the inherent time scale. That's what I want to say. Okay, okay. So this t is done. Then what do we have? We have maybe a non-dimensional length scale. Let's write it as what? Let's write it as, what do we write? So maybe I'll just write that this divergence, the non-dimensional divergence or the gradient would be basically the dimensional one, okay, divided by the characteristic length, which is LC. Okay. So if we just invoke these scales, let's not like pinpoint what this UC, TC, and LC would be. Just like just let us keep it general, because we just want to derive the equations. So if we just use this in this NS and the continuity equation, then what do we get? So I think we have done this many a times. So we'll get, this is rho. This term would be what? It would be UC. Okay, this would be UC by TC. Okay, into del U by del T, and this is the vector, of course. Plus this term would be what? It would be QC squared by LC. Okay, into U dot grad U. Okay, and this term would be what? It will be minus PC by LC. Okay, it's just PC by LC into this gradient of pressure, and then we have what? We have mu QC by LC squared, okay, into del square U, which is basically the viscous term. All right, so now let's let's now choose the pressure scale, and let's say we choose the pressure scale to be, since we are deriving equations for the creeping flow analysis, let's now choose the pressure scale to be, so what do you choose as the pressure scale? Do you choose advection time scale or the diffusion time scale? So do you remember what do we need to choose? Yeah,
Diffusion.
yeah, exactly, diffusion time scale, which means, do you remember what was the diffusion time scale?
Mu C U C by L C.
Yeah, exactly, so it's mu c uc by lc. Exactly. Okay. So we'll choose PC as just this mu c uc by lc, and then let's derive the non-dimensional equation of this dimensional equation. So let's first write PC as mu c uc by lc. So this term would simplify as what? This term would simplify as mu c uc by lc squared. All right. Okay. So what I will do is I will now multiply the entire equation with what? With LC square by mu UC. Okay. and see what do we get. So the first term, and I bring this row inside. Okay, I just bring this row inside. So what do we get? I get rho times UC by LC. Sorry, this is not LC, this is TC actually. Into, it is LC squared by mu UC. Okay, into this term, del U bar by del T, plus next term is what? Next term is UC squared by LC into, this is what? This is LC squared. Okay, this is LC squared by mu times UC. Okay, please check the algebra if I'm making any mistake. And this is U dot grad U. Okay, and the right hand side is just because I have divided the entire equation by the reciprocal of this term basically, and this term is basically equal to this term. So the right hand side would just end up simply to be gradient of pressure plus, I think it is just del square of U. Okay, and now let's simplify the left hand side. So this term would be what? Basically this is this. Okay, and what is that? So basically this term would be what? So this term would be what? So this is UC and this is UC. Okay, so there is one UC here, and yeah, I forgot there would be a row here also because this row is multiplied to both these terms. Basically, this row is multiplied to here. It will also go to there. Okay, so that's why there would be a row there. So let's just write. So this one UC and one UC goes from here, and one LC and one LC basically goes from there. Okay, let's see what we get. So this term becomes rho times LC squared, okay, by TC into mu, okay, into del U bar by del T plus this would be rho times UC LC, okay, by mu into U dot grad U, okay, okay, and this would be minus gradient of pressure plus del square Q bar. All right. So now let's do one thing. Uh, what shall we do? So let's for the time being take TC, okay, to be the advection time scale only. Let's now take this TC to be the advection time scale. So then can you relate TC with UC and LC? So what does TC becomes then? This would be what? Can you tell me? What does TC become? If I choose TC as
L
the, yeah, exactly. So this
LC by
becomes
UC.
LC by UC, okay? Which means if you simplify this term, basically, you will see that this will be Reynolds number, okay, times del U bar by del T plus Reynolds number is evident from here, okay? So this becomes Reynolds number times U dot grad U, and this would be minus gradient of P plus del square V, okay? I just take the Reynolds number outside, and then this would become del U bar by del T plus U dot grad U is basically minus gradient of P plus of del square V. Okay, so this is the non-dimensionalized Navier-Stokes equation, uh, as you can see. Okay, so now the idea is in the limit, okay, in the limit Reynolds number tends to 0, what do we have? We have, so if Reynolds number tends to 0, this means that this term will cease to 0, okay, which means I just have this minus gradient of P plus del square V is basically equals to 0. And this equation, and of course, along with the fact that divergence of velocity field is equals to 0, which is basically the continuity equation. So these two equations Okay, these two equations are known as creeping flow equations. Okay, or sometimes they are also known as the Stokes flow equation. All right. So is this clear or not? Like what in the limit of Reynolds number tends to 0, it's the fact that when Reynolds number basically, it's not exactly 0, you can approximate it like this Reynolds number is tending to 0. Like for the case when, for let's say for the case you are examining the flow of flagella in a let's say unbounded medium, you can approximate the Reynolds number to be a very less or in fact the Reynolds number indeed comes out to be a very less value of the order of 10 to the power minus 4 or 10 to the power minus 3, for which you can invoke the fact that this is very close to 0, and you can thus neglect the inertia terms that appear in the Navier-Stokes equation, which means in the creeping flow regime, the momentum equation is nothing but the balance between the pressure forces and the viscous forces. Okay, so it's the gradient of pressure that balance the viscous forces that arises due to the viscosity, due to the viscous nature of the surrounding fluid. Okay, but more than the I would say more than the equations, there is one very fascinating aspect of this creeping flow equation. So can you tell me, just 1 second. So can you tell me what is the major difference between this equation and this equation?
Creeping flow equation are linear.
Yeah, exactly. This means, so that's one of the, like it's a great plus point that nature has already provided us, which enables us to have some solutions which would otherwise would not be possible if we have that inertia term. Okay, so one important consequence of these creeping flow equations, okay, one important consequence of these creeping flow equations are that they are linear basically. So they are they are linear actually, and this is very important, and this will we will see that because of this consequence of linearity, we can uh directly like infer certain things which would otherwise be impossible if we had that inertia term in the Navier-Stokes equation. Okay, so and that consequences we will see, but like till this, if you have any doubts you can ask me, but I would just also show you one more thing, that what if we don't choose this TC at the as the advection time scale. Okay, let's say we don't choose this TC, I mean so here we have chosen this at the advection time scale. Let's say now we have a time scale which is an inherent time scale. Okay, and then what happens? This means that what I'm saying, that let's see if, so this has nothing to do with creeping flows, but I just want to show this out here. So if I'm saying that TC, instead of writing it at LC by UC, it is not LC by UC, it is just some prescribed value. Okay, if TC is already prescribed, then let's see what do we get. Okay, if TC is already prescribed, for instance, let's say a microorganism flagella move its tentacles with some angular velocity omega. In that case, TC would be just omega inverse, right? This means we have a prescribed time scale for this problem. Okay. Yeah, I'll just write it as left TC is prescribed. Okay. Then let's say how this basically how this equation basically changes. Okay, let's see. So we'll just focus on this term because the other terms does not have any time dependency on it in it. So we'll just focus on this term. So this term would be what? It would be rho times LC squared. Okay, let's see this. So it is rho times LC squared by TC times what? I think I have an U here maybe. Sorry, mu. Okay, it is rho LC squared by TC times mu. Okay, all right. So now what we will do is we'll do the following. I think I made a mistake here. There should be a U. Shouldn't there be a U? No, that U gets cancelled out. So I think it's rho times. Okay. So it's rho LC squared. Okay. All right. All right. Okay. Nevertheless, yeah. So what now we will do is we'll do something like this. So we will multiply this with a UC. We'll multiply this with an UC and divide it with an UC. Okay. And let's see what we will end up to. So we'll just write rho LC UC by mu into LC, okay, LC by TC times UC. This we can do, right? Because there is an LC squared. So one LC squared is taken here and one LC squared is accounted in this term. This UC is basically taken here. Basically, it's taken here. So this UC goes there, and then we have this UC, and then we have this TC. Okay. Then can you tell me what is this number? What is this?
Reynolds number.
Yeah, so it is Reynolds number, exactly. And then this term can be written as LC by UC into TC. Okay, which means what is this actually? This is actually the advection time scale to the characteristic time scale. Okay, and so it's just the ratio of two time scales. Okay, and we expect that since now we have two different time scales, see it's so the scaling analysis is very like similar. Okay, recall the earlier problem. So we had two time scales in velocity. You remember there was this porous this suction velocity as the characteristic radial velocity, and we had that tangential velocity as the characteristic theta velocity. And then since we had two scales, we are bound to get a term which will involve the strength of one characteristic value with the strength of other characteristic value. Similarly, in this case, if we have two time scales in our problem, one is the advection time scale, which will arise because of the flowing nature of the flow, and one time scale, which is basically the inherent time scale that we have for our problem. So this means we are bound to get basically two time scale, which will dictate the ratio of one with respect to, which will dictate the strength of one with respect to the strength of the other. And this ratio, okay, this ratio of this characteristic time scale to this advection time scale is given by a non-dimensional number. This is known as a Strohal number. Okay. I don't actually remember the exact spelling. I think it is something like this. So it is known as a Strohal number. I'll check. I'll quickly check what exactly is this spelling. It's not a good practice actually to write wrong. Just give me 1 second. So it is Strohal maybe. Yeah. So it's called. Yeah. So it's called as a Strohal number. Yeah. Yeah. I think the spelling is correct. S-T-R-O-U-L. Anyways, this ratio of this, so I think now you encountered another non-dimensional number, which is basically the Strohal number, which is nothing but the ratio of the characteristic time scale to the basically the advection time scale. Okay, now if I write the non-dimensional equations now, then this would become what? This would becomes Reynolds number times 1 upon Strohal number. This is written as SR, okay, or it is written as ST into del U bar by del T bar plus Reynolds number into U dot grad U, because the other terms would basically be the same. Okay, and this would become minus gradient of pressure plus the viscous term. Okay, so this is interesting, right? Because now just by changing the time scale or of the problem, and by bringing two time scale, we end up getting one more non-natural number, which is basically the Strohal number. In either of this scenario, if we invoke the creeping flow assumptions, because we have Reynolds number both multiplied with these two terms, we'll anyway end up getting this, just getting the terms on the right hand side, is that there is a balance between the pressure gradient with the viscous forces. But the idea of this exercise is to just show you this: if we choose if we choose different scale, we end up getting different versions of the same dimensional equation. We end up getting different versions of these non-dimensional counterparts. That's the idea that I want to basically put it here. Okay, so I hope this is clear. But anyways, here also, like, the idea is if we invoke this Reynolds number going to infinity, we will end up getting the creeping flow equations. All right. So we'll stop here for some time. If you have any doubts, you can ask me. I'll just come in a few minutes. All right. Sorry for the interruption, guys. Right. So, yeah, if you have any doubts, you can ask me, or else we will now see one important aspect of creeping flow equations is that the consequence of linearity, as you have rightly pointed out, into some interesting examples, which would otherwise can't be inferred if we have the inertia term in the momentum equations, basically. Okay, but before starting, I'll wait here for a couple of minutes. If you have any doubts, you can let me know. All right. If you don't have any doubts, let's consider a first example into understanding what the consequence of linearity brings in. Is that let us try to understand the drag on bodies that are mirror images in a direction of motion. So what I mean is that in the limit of low Reynolds number flows, if I want to estimate, let's say what, just 1 second. So let's say I want to estimate the drag on a conical object which is basically placed in a uniform flow. Okay, when it is coming with a far field velocity u, as you can see from this figure. So the idea is that before like quantitatively computing the exact magnitude of the drag force, the question that I would put forward here is that if I now have a similar scenario where I now place a mirror image of this cone, okay, into the same flow, okay, into the same flow in the creeping flow limit, the question is which objects, that is object A or object B, would experience a higher drag force. Okay, that's the question that I would put forward here. You need not need to do any calculations. Okay, you need not do any calculations on the drag force, because doing evaluating drag force of this conical object is a little tedious. But using the concept that we saw, okay, and the fact that this object is a mirror image of this, or the other way around, that this is basically a mirror image on this. Can you tell me in the limit when Reynolds number basically goes to 0, or in the limit of creeping flows, which one of either A or B would basically experience a higher drag? Can you tell me? Think about it. Uh, think about the problem first. You may take some time of your own, but can you guys just come up with the answer on this? Yeah, so you can give it a try. It may be wrong, but there's nothing wrong in giving it a try. So what do you suggest that uh, so intuitively, how what does it what so intuitively, in from our present day experiences, which one will basically have a more drag? Will it be A or will it be B?
B.
B, right? So see, so this is simply because, like, from our general notation of streamlines, this object appears to be more streamlined, okay, in the direction of flow. And this appears to be a blunt object first in the direction of flow, and then this just goes into so it gets tapered in its wake region. But this is not the case. I would say this is not the case in the low Reynolds number flows. And I would say in the limit when Reynolds number goes to 0, the drag experienced by A, which is dA, and the drag experienced by this dB, object B, is exactly the same. That's that's the whole idea. Okay, and I will say like qualitatively I'll try to explain why is that so. So let us now consider the case A. Okay, let us now consider the case A. So for the case A, what are we going to solve? So for in order to evaluate the drag, what are we going to solve? So we are solving the creeping flow equations, right? Which means that this gradient of pressure is basically balanced by this viscous force. Of course, we also have this equation. Okay. And these equations are subject to what? So these equations are subject to the fact that the velocity field u is basically equals to the far field velocity. Okay. At, let's say, any radial location infinity, and this u is basically equals to 0. Okay. At what? At r equal to, I would say at r equal to on the surface. Maybe I would just write it at r equal to some s of a, where s of a basically denotes the surface. So precisely for case A, we are exactly going to just solve these equations subjected to these two boundary conditions. Okay. Now for case B, okay. Now, like before going to case B, the solution that we are going to get, okay, the solution that we are going to get from these by solving this equation, however or whichever way we seek to solve, is basically that we are going to get the solution as something like this. So what are we going to get? We are going to get the solution of the velocity. We are going to get the solution of the pressure. Okay. So I think I'm clear in explaining it. Now, if we go into the case B, so what do we solve in case B now? We exactly solve these equations in case B, right? It's just the same thing, right? So we solve these equations. Okay. So we solve these equations in case B. Subject to what? Can you tell me? Particularly the boundary conditions now in case B.
Same.
It's the same, right? Because the objects are the same. Okay. So I'll just write it at u at is equal to u, and this u basically goes to 0. Okay. So this is at infinity and this is on the surface. Now, here is the point. Okay. Try to understand it. Try to understand what I'm going to say. Can case B, okay, be replicated? Can we replicate case B by changing the direction of flow of case A? That means if I keep this same and I now say that okay, in now I want to have a flow which is basically moving from right to left of our basically from right to left instead of moving from left to right. So if that is the case, can we replicate case B from case A? Is this an yes or a no? Can you tell me?
Yes.
This means that if I reverse the direction of flow of case A, I exactly end up getting case B, basically. Okay, now what I mean to say is, so what I mean to say is, if I just change the direction of far field, okay, just the direction, okay, this means I exactly end up getting case B, which means that if V and P, so what I am saying that if V and P are solutions of A, okay, then I would say minus V and minus P, okay, would be the solutions of B. And this is only possible because the governing equations are linear. Is this clear or not? Or there is some doubt? Yeah. So this means that we can deduce this from this because only the fact that these equations that we have are linear, and this is one of the most important aspect if we have linear partial differential equations. Okay. So the bottom line is that if we now have two mirror objects, if we now have an object A and I have a mirror object, I have a mirrored object of that object A placed in the direction of flow, both these object would basically experience the same drag force in the limit of like low Reynolds number hydrodynamics. Now, why it differs from our intuition, that intuitively it feels that these objects would basically experience a larger drag. That is solely and solely due to the inertia of the fluid. Okay, it's the inertia which actually makes it which is actually responsible for having different drag forces in these two cases. Okay, if we do not have inertia, the fluid actually does not, it's just that the fluid actually does not care about what is the contour of the object if the direction of the flow is basically reverse. That's the whole idea of this problem. Okay, this means, yeah, so this means that so the idea is that this is only due to the consequence of linearity that we can that we bring to the picture. The idea is that the direction of drag force will be opposite for this case B, but its magnitude will be same. That's, so you need to appreciate that. So if I, so it's obvious, right? So in this case, if the flow is flowing in this direction, okay, the drag force would be what? So what would be the direction of drag force if the flow is basically flowing from left to right? Can you tell me?
Right, right to
Yeah,
left.
right to left, exactly. So drag force will be is in the will be is in the direction. So if I want to replicate case B, as I said, I will just make this flow coming from here, which means the direction of drag force would be in this direction. But in magnitude, the two drag forces would exactly be the same in the limit of Reynolds number tending to zero. So that's the first idea that I would like to put forward here, and it's the first consequence of linearity. Okay, we'll move into the second consequence. So in the second consequence, we will see that in the limit when Reynolds number tends to zero, what is the lift, okay, that a sphere would experience, okay, in a simple shear flow. Okay, so I think you know what is a shear flow, right? So any flow which is basically of this nature, okay, so the flow field is basically linearly varying along the cross field direction is known as a shear flow. Okay, so the idea is again in the limit of creeping flows, okay, what is basically the lift that a sphere which is already rotating with some angular velocity omega would experience. Okay, and yeah, so this is the question. And can you tell me the answer now based on the understanding that the governing equations are linear? Can you tell me what is the lift? How much is the magnitude of the lift
Zero.
that, yeah, zero, exactly. Why is that
Zero.
zero? Yeah, why is that zero?
Pressure field will be symmetric about both
Exactly. Pressure
both
field,
plane.
the pressure field would be symmetric. Yeah, that's a consequence, I would say. True. If lift is zero, the pressure field would be symmetric. That is true. But uh, so I would say that is not, I mean, that is not wrong. That's correct. But I would say that's a consequence of the fact that the lift is zero. Okay. But why is the lift zero? Is because again, as I said, that is because of the fact that the governing equations are again linear. Okay, and because the linearity, as I have said, we can decompose the entire problem into three simple problems, as we have seen, as you basically saw in this figure. So what we will do is we will decompose this problem as you basically, so I hope this is visible here. So we'll decompose this problem into three simple, oh, sorry. So this is the problem into three simple problems. Okay, one problem, there is just a sphere which is rotating with some omega. Okay, so there is just a sphere which is rotating rotating with some omega about any arbitrary axis in a stationary fluid, plus there is a sphere which is stationary in a uniform flow, plus there is a sphere which is stationary in a simple shear flow whose center essentially coincide with the center of the sphere. So if you just add these three cases, you will just end up getting this case. You can just verify and see. So do you agree this do you agree with me or not on this point, that you can decompose this problem into three simpler problems?
Yes.
Yeah. So now let us try to investigate the lift associated with the three cases separately. Okay. So from case A, can you tell me what will be the lift on the sphere in case A? So if there is a sphere that is just rotating, okay, around any arbitrary axis, let's say this is the axis with an angular velocity omega, and the fluid is basically stationary. What is the lift? What is the lift force on this sphere? So you have already so you have already answered that.
Uh,
Yeah, it's zero, right? It's zero.
yeah, yeah.
Yeah, that is simply because, as you have already said, in order to have a lift, okay, we need to have a breaking of symmetry, as you have correctly said. Okay, now in this case, there is, so it's symmetric in all possible directions, right? It's symmetric. It's symmetric in all possible, let's say, unit vectors that it might have. Okay, which means there is no breaking of symmetry in case A, and that's why the lift force in case A will obviously have to be equals to zero. Can you tell me what is the lift force on case B? Can you tell me? That is also zero, right?
Zero.
Yeah,
Yes.
that is also zero, right? Because in order to have a lift force here, again there should be this breaking. So this is something called as a 4F symmetry breaking. Okay. So this means that if there is this flow in this direction, okay. Now if I reverse the direction of the flow, okay, if there is the breaking of symmetry in this case, then only this sphere would experience a lift in either up or down direction. Because so the idea is, see, the idea is here is very simple. Okay, if the sphere, let's say, move up, let's say if the sphere move up, if there's a uniform flow in this direction, which means if there's a flow in the other direction, the sphere has to move down, right? But then what distinguishes this direction? Because these are basically the same only, right? I hope you get what I'm trying to say. Because apart from the direction, it's exactly the same, that the flow of the same magnitude is just coming from one particular direction to the other, which means that if I just reverse the direction, we cannot have a symmetry breaking in this scenario, which means that the lift force again would be equal to zero. Similarly, for case B, sorry, for case C, the lift force will again be equal to zero. Again, this is because of the fact that flow this flow cannot cause a lift of the sphere, again because of the symmetry breaking, which means that if I now have a flow of this sense, okay, if I now have a flow, oops, let's say now I have a flow of this manner, okay, let's say I have a flow basically, okay, I will not say like this, let's say, how do I say it? Let's say I have a flow in this direction, so there is this flow coming here, and let's say there is this flow which is basically going in this direction. Okay, so this and this is basically the same, but it is just opposite in the rotation sense, that the sphere would rotate. So if this flow basically rotates the sphere in this direction, the other flow would basically rotate the sphere in the counterclockwise direction, but it's the same thing, right? So this means that there isn't any symmetry breaking as well for case C. And since the individual lift of all these cases is equals to zero and the governing equations are linear, this means I can superimpose the solution of these three cases and the total lift force L. Okay, and this would be a vector because force is basically a vector. The total lift force is basically a summation of lift force of all these cases, and the total lift force would basically be equals to zero. Okay. But this cannot be done. This cannot be done, okay, in the case where there is this inertia term, because inertia term essentially brings non-linearity into our problem. And even if in the inertia, so if there's an inertial flow, okay, if there's an inertial flow, even if the individual components lift may be zero, but you cannot then sum it up because superposition won't work in a non-linear problem, and that's why the lift force may not be equal to zero. And in fact, the lift force in this case, if there is a inertia flow, is essentially not zero, and the fluid moves, and it is shown that, so there is a very nice paper by Ho and Lil. Okay, I think this is the lateral migration. So the paper was something like this. So the paper suggested that there is essentially a lateral migration of a sphere when it is basically subjected to a unbounded shear flow, okay, in the limit of weak inertial case, that if there is the inertia that is present, and even if that inertia is weak, the sphere would basically suffer a lateral migration. Okay, so that's the idea. But if there is no inertia, or when Reynolds number is basically equals to zero, the individual lift would basically be zero, and then you can superimpose the entire problem, and your entire solution would have a case where the lift force is basically zero. So is this clear or not? So these two examples, I think these two examples are sufficient to acknowledge the fact that how the linearity of certain PDEs, or how the linearity of certain partial differential equations helps us in qualitatively, solving very complex problem into making them as simpler ones. Okay. All right. Similarly, can you quickly tell me what will be the lift force on this case if there is a parallel flow between a channel? That is also,
Zero.
yeah, that is also zero. That again holds the same 4F breaking symmetry principle, because since it is symmetric, uh, you do not actually have a distinguishment between the flow that is coming from the left to right or the flow in the other sense as well. So that's why this lift. So here also the lift force would basically be equal to zero. Okay. All right. Okay. So I hope this is clear. So I would end today's class by discussing something which is known as a spherical coordinate system, because in the next class, maybe we'll solve a problem in the creeping flow limit where we will essentially calculate the drag, okay, or like we'll calculate the drag that a sphere would experience in the presence of a background parabolic flow, as we have seen in this case. So what happens if there is a background, if there is a sphere in the presence of a background parabolic flow, and we will try to calculate what will be its drag force, and for that we will use the creeping flow equations. Okay, that drag force in magnitude is similar to the one that you derive in the class, that 6 pi mu lc that you derive. But we will again, like, since it's a different flow field now, we will again revisit how it can be done. We will use the stream function approach as well, and that is essentially very interesting, the stream function approach. We will also see a theorem which enables us to calculate the drag force very easily. So we will all see this in the next class. We'll keep it from the next class. But for that you need to know the spherical coordinate system. And here, before ending today's class, I will uh, before ending this class, I will just quickly recapitulate the spherical coordinate system. Okay. So the spherical coordinate system basically looks something like this. So we have a z axis, which is the same cylindrical, and the Cartesian z axis, which is basically facing in this direction. First, we will lay out the Cartesian system here. So the Cartesian system is basically like this. So which one would be x? So this has to be, I think this has to be the x axis, because x cross y only then point z in the upward direction. Okay. So this is x, this is y, and this is z. So this is the Cartesian system that we all know. Okay. Now in spherical system, oops, I think my screen has just stuck. I don't know why. So can you see my yeah, okay, now it came. Okay, okay. Okay, all right. So in spherical system, so can you tell me what are the three coordinates that we have in a spherical system? Do you know that?
R theta phi.
Yeah, exactly. So this is r, this is theta, and this is phi. Okay. So the r coordinate. So I think you guys know what the spherical coordinate is. So that's well and good. But anyway, it would help you to recapitulate what you know. So the r axis in spherical coordinate system is basically this r. Okay. I don't know why there is a lag in my screen, but okay. Okay. Now, can you tell me if you know which one is theta? So now, as you see, there are two angles. This is one angle, which is basically the orientation of this r-axis with respect to the z-axis, and then there is this angle, that how the projection of this orientation would change with respect to the y-axis, with the x or the y-axis. I mean, if you know with the x-axis, you can anyway calculate this with respect to the y-axis. Okay. So can you tell me which one is theta basically? Which one is basically theta?
Theta is with respect to xy plane. What is the angle?
Yeah,
Projection.
yeah, but
Projected.
yeah, so anyways, you can name anything as, and so you can name any
Ah,
axis, yeah, and with that, but for the sake of convenience, we will name this angle as theta. That theta is basically the angle that the radius vector makes with basically the z-axis in this sense, okay, in this sense. So now, then what is phi? Phi is essentially called a polar angle, which means if I now take a projection, okay, if I take a projection of this radial vector, then what would this be? Can you tell me what would be this length? It's very simple. It's just trigonometry. Okay.
R
Yeah.
sin theta.
Exactly. So this length is basically r sine theta. And can you tell me? what is r sine theta in cylindrical coordinate system? Can you tell me? Can you relate r sine theta with something in the cylindrical system? Not spherical, I'm talking about cylindrical system. Just think about it. Just think about this.
R.
Yeah,
It's
exactly.
like R.
Yes. So this means r sine theta is nothing but the cylindrical radius. That's what you say. So we will denote. So in order to distinguish the nomenclature, we will denote the cylindrical radius as rho. So this is obvious, right? Because a cylindrical system have the r theta plane where so the r theta plane coincides with the xy plane, right? This means that the cylindrical radius is something like this, and this is nothing but the cylindrical radius with the axis of the cylinder placed something like this. So this is the cylindrical system, right? So this means this r sine theta is nothing but the cylindrical radius. Okay, and now this phi, as you see, this phi is actually measured in this sense from the x-axis. Okay, all right. So then in terms of r, theta, and phi, can you tell me what this x-axis or this x, I would say what this x vector would be in terms of r, theta, and phi now? Can you tell me based on your geometry, based on this trigonometric picture?
R sine theta cos phi.
Yeah, exactly. So this x becomes r sine theta cos phi. Okay. Similarly, you can show that your y becomes r sine theta sine phi. Okay. And your z essentially becomes r cos theta. Okay, and this is essentially the relations between the cylindrical coordinate system with the, sorry, the relation between the Cartesian coordinate system with the spherical coordinate system. Okay, so this is nothing but your Cartesian to spherical, what you say, conversion, I would say. All right. Similarly, you can have, from this picture only you can derive all the conversions. You can have a Cartesian to cylindrical conversion, you can, that you all know. You can have a cylindrical to spherical conversion, and so on and so forth. All right. I would end this by asking one final question, that if axis symmetry in cylindrical coordinate means that your variables are independent of theta and its gradient, then what does axis symmetry means in spherical coordinate system? Can you tell me that? So, or yeah,
Independent of theta and phi.
independent of theta and phi both.
Phi.
Yeah. So yeah. So it's independent of theta or it's independent of phi. That's
Independent of
yeah. So anyways, I mean it's a good try, but I'll tell you the answer. So what does axis symmetry means? This means that if I move around any axis, okay, if I move around any axis, the name suggests that my variables would be independent of its like coordinates basically. Now, in spherical coordinate system, okay, my axis of symmetry is what? It's the z axis, right? So if I have a sphere, if you can visualize, if I have a sphere here of something like this, and if this is the radius, then the axis of symmetry, of course, a sphere have infinite axis of symmetry, and one such axis of symmetry is the z axis, which means if I move around the z axis, and if I say that my problem is axis symmetric, this means this means that my variables will now be independent of what? Will it be independent of theta or will it be independent of phi?
phi.
Exactly. And you can visualize something like this. So let's just draw a, let's say I draw a tennis ball here, let's say. Okay. Let's draw this and let's see. So let's say this is a ball, maybe. Let's say I draw a ball here. Now it looks more like a ball. Okay. All right. So now if I have this z axis, which is basically pointing in this direction, okay? Let's say it starts from here and it's just pointing in this direction. Okay, this means that if I now move around the z axis, I have these. So this means that if I move around so if I just move around the z axis, where Ez is the unit vector of the z axis, this means I'm moving around in these directions. Okay, I cannot show what is happening behind the ball, but I'm just moving around these directions basically. Okay, either I am moving this way or this way, that depends on which sense you are looking at. So now this means that if my problem is axisymmetric, then let's say I'm telling that my problem is axisymmetric, and let's say I'm focusing on one variable, let's say u. This means that if I move around these red dotted lines, my u will essentially be the same and it will not change. Okay, and that is actually the meaning of an axisymmetric problem. Okay, so so this is the meaning of an axisymmetric problem in spherical coordinate system. So the idea is that in spherical coordinate system, axisymmetry means all variables are, I would say, independent of the polar angle phi and its derivatives. All right. So this is something that I wish to convey here. Okay. So with this, I would stop today's class. If you have any doubt, you can feel free to like speak out, or you can post it in the discussion forum of the group as well, in the course website, and we in the team will be happy to address it. If you don't have any doubt, we will meet in the next week, where in the next week we will try to solve one problem that is associated with this creeping flows, and let's see how far we can progress from it. Okay. uh, all right, if you don't have any doubt, thank you for joining this session. uh, I'll close it now, and we will meet in the next week. Thank you once again. Okay, so I'm closing this session. Thank you. Stop today's class. If you have any doubt, you can feel free to like speak out, or you can post it in the discussion forum of